All right. Thanks, guys, for ladies and gentlemen, I suppose, for coming. We're going to talk a little bit briefly in this lightning talk format about storage for data platforms and the different types of storage you need to provide to kind of data platform engineers so that they can successfully run data-intensive applications in an OpenStack-like environment. So the biggest thing, the biggest takeaway is you want to provide the data platform engineers and the people that are consuming that platform on top of it kind of a common experience across both the public and the private cloud. And so when you're trying to build kind of a catalog of services that you want to expose to the data engineers for building these platforms, you need to kind of look to the public cloud and kind of mirror the types of services that they have exposed for folks to compose these different data platforms. So the three main pillars that are necessary for data platforms are object, of course. In the public cloud, you have Amazon S3 or Google Cloud Storage. In the private cloud, you see people using Ceph or OpenStack Swift. There's persistent block. In the public cloud, this would be your Amazon EBS, your Google persistent disk. And in the private cloud, most commonly we see people using Ceph with RBD. And then an often forgotten portion is some sort of really low latency local block, right? So in Amazon, this would be your X1 or i3 instance types. It would be a local SSD in Google Cloud. And you really want to provide all three of these because they each serve kind of important purposes for folks that are building data platforms on top of your infrastructure that you're providing. So object is where the vast majority of the data goes. It's where the volume is. And it's really for when data needs to be persisted and shared between tenants or different clusters. So one of the patterns that's emerged with data platforms in private clouds or in public clouds as well is provisioning multiple different analytic environments inside of the public cloud. And instead of each of them handling their own storage requirements and then having to copy data sets in between these different clouds and having to rehydrate data and track complicated lineage relationships between the different copies that are in these different storage silos, instead you kind of persist all the storage back down to a common object storage layer. And then that way you can access the data in situ. You don't have to worry about copying data around or all those kind of complicated things. And so we're talking about many petabytes of data. So using something like erasure coding for storage efficiencies really makes sense here. You don't want to be storing 3 copies when you have petabytes of storage. And it's very high throughput, many gigabytes per second of ingress and egress traffic. So the object workloads that we're seeing in terms of data platforms, people have streaming applications that are checkpointing data into object storage, people storing kind of Hive, OLAP cubes, analytical processing data into the object store using columnar formats like Parquet or ORC, or even large corpuses of data that they're then going to run and train machine learning models on. But also, even outside of kind of the big data space, people need a place for storing large amounts of media files, whether it be images, audio, video. I'll leave it to Federico to go into the other aspects.
So another type of storage that we have in both public and private cloud configurations is, of course, block. You need block to be able to back your virtual machines, of course. But besides the runtime of the operating system, you also have to deal with the literal data aspect. So you have the big data in object, but you still have databases. Let's call that little data for now. And here you have latency requirements. So you have to have block that is performant within certain latency requirements so that you can run a database successfully. This typically in Ceph is done through capacity planning in combination with OpenStack, so that a certain number of IOPS is made available to a virtual machine by throttling access at the Cinder level. The easy way to think about this is the Amazon AWS model. In Amazon AWS, you don't just provision storage. You provision storage and IOPS as a single dimension. As you allocate storage, EBS also gives you IOPS for the right storage classes. That is the right way to think about enterprise storage. Unless you're talking about a laptop where the vendor figures out what the IOPS requirement is and you just figure out the capacity. For enterprise, you always have these two dimensions. So Amazon has simplified this by giving you one-dimensional mapping for these two quantities. We can do this with OpenStack by using Cinder to reduce the amount of IOP that we leave a virtual machine able to do, so that we can simulate QoS through a capacity planning exercise. Kyle and I have given a full talk on this last year. It's a much bigger subject, but there is documentation on how to do it. The block layer has multiple abilities besides this. Once you are able to run the database, you can use the block layer to ameliorate the operation cycle. So you can manage backups with snapshots, or you can detach and reattach the storage as you're replacing the instance, if you're doing a vertical scale up, so to speak, of the instance with a bigger instance. And also it gives you the ability to attach an arbitrary amount of storage, which is convenient. You don't have to have a fixed amount of storage per instance. This quantity comes from the network, and so you can customize the amount of storage that you're using with your specific instance. Typical users for these are the entities that you would see provided by Amazon Aurora, so Postgres, MySQL, MariaDB, and so on. These have certain latency requirements, but they are fairly well-behaved databases that we are able to host with Ceph successfully. Besides the block provided by the distributed system, there is another type of block, as Kyle was mentioning earlier, which is directly attached block. Now, a distributed system will never be able to beat a directly attached type of storage in terms of latency. There is simply no way. There is a network in the middle. So in certain cases where performance is essential and the scalability or the resilience of the storage is not relevant, you can use a local, very fast storage medium like NVMe to provide that capability. This is what in Amazon we would call ephemeral instances. They don't give you persistence. They will go away when the virtual machine disappears, but they can give you the highest level of performance. This is used for scratch data, typically, data that you don't need to keep, or for capacity overflow if you're running out of space. And the typical examples of this are Cassandra. You want to have very fast local storage for Cassandra, but you don't need to provide resilience to the data. If a node disappears, Cassandra will deal with it for you. And now Kyle will wrap it all up for us.
So again, kind of going back to the three pillars, you see them present in the public cloud by way of either Amazon EBS or Google Cloud Persistent Disk for block storage, S3 or Google Cloud Storage, being comparable with Ceph object storage, and then finally low latency block. That would either be various instant flavors in Amazon or local SSD in Google. But in the case of OpenStack, you would do that by way of PCI pass-through of local NVMe devices and configuring instance flavors such that the people constructing data platforms kind of have this menu of services that they can use to pick and build, whether it's dealing with small amounts of data and they want kind of a persistent volume, whether they need a large volume of data and object makes more sense, Or finally, if it's, they have a distributed application that's handling its own durability and persistence, maybe a local really fast NVMe is the right tool, or if it's just kind of ephemeral data, Scratch or intermediate overflow from a MapReduce or Spark application, you want it to be fast, but you don't care so much about the resiliency. So that's it. Thank you, folks.